what do you do when you have an equation like, let's just say you're given that tan theta is equal to the square root of 3. You're given that and you're asked to find out what theta is. Now, I'm in the video. Hello. Now, what you have to do as well, you can all wave. Hello. Okay. What you can do is you can, you also need to know the domain of theta as well. So remember that the domain for the trig functions are a set of angles, and the range is just a number, right? Between -1 and 1 for sine and cos, and between -infinity and infinity for tan. When you look at the functions, you'll see why. But if you remember that tan is basically like a gradient, right? Then the gradient could be flat, which would be 0. Oh, there we go. Flat, which could be 0, or it could be a really steep graph. Okay, a really steep graph, which would be like close. The steeper it gets, the closer to infinity it gets, or it could be negative, so going down slope. In which case, it's getting closer and closer to negative infinity. Okay, so tan, if you think of it in terms of a slope, really could be any number at all, but sine and cosine is limited to coordinates between 1 and -1. Okay. By the way, Sam, I don't know whether you caught up or not, but all the videos are on Google Classroom if you need them. Yep. Okay, so we've got tan theta equals root 3, but you also do need a range, and it's going to give you a nice simple range for this one, and that is that theta is between 0 and 2 pi. So it's in that first rotation. Okay, all good so far? So here's a solution for it, and then I'll get you to do question 4. So what we do first of all is, you know what? I might make it minus root 3 just to make it a little bit more interesting. Minus root 3. So the first thing we do is we sort of go, okay, it's minus root 3. So I draw my little unit circle axes and I say, which of the 4 quadrants is tan negative? And if you remember the old all students take care, and that's quadrant 1, 2, 3, and 4, which quadrants, you can yell it out, which quadrants is tan negative in? Sorry? Not quite. And can you refer to them as quadrants? Quadrant 4, where only cosine is positive, and quadrant 2, where only sine is positive. Not the A1, Lily, because all are positive there. Yeah. Okay, so it's only those two. So that's what I do. I don't do the cast. I don't do the letters. I just do an axis and put ticks in the spots. Now, I know that a number of you, many of you, maybe all of you, can probably keep this information in your head. But I can say, as someone again with a maths degree, someone with 20 years teaching experience, I still draw the little axis. There's something visual that eliminates errors by keeping it in my head. So I encourage you guys to do that too. So we know that it's in those 2 quadrants. Next thing what we do is we work out tan of theta hat. Now theta hat, remember, is the reference angle. It's the quadrant 1 angle effectively, but it's probably let's just think of it just like the acute angle. And with the reference angle, we don't worry about sine. So we say if tan theta hat is equal to root 3, then what's theta hat? This is an exact value that we're supposed to know or be able to work out the angle really quickly. So it's root 3. So I know that the 45-degree one is the ones with root 2's in it. So I know it's not that triangle, so it has to be the other triangle. Lily? No. So tan theta hat, whenever we take the sine, cos, or tan of theta hat, we ignore the sine and we just look at that value. It's as if it was in one of those triangles. So it's an acute angle, so therefore it's always positive. Okay, so all we're doing here is we're working out the unsigned value, and then we go back and sort it out from there. Does that make sense? Cool. So again, not knowing very well my trig values, even though I've been saying them ad nauseum, I know it's going to be in that half an equilateral triangle. So I stick one down really roughly. I know that the side length is 1, so that makes that a half, and that makes that root 3 on 2. And then I know that that one's going to be 60 degrees down here. So that's pi on 3, and that's pi on 3. Okay, now I just need to work out which one is going to give me root 3. So I know that if it's not one, it's the other, right? So I've got obviously a bit of experience, so I remember which one it is, but we know it's opposite over adjacent. So we've got opposite over adjacent, opposite over adjacent. But I feel like it's going to be this one because the root 3 is on top already. I'm just trying to unpack my thinking. So then I'm sort of quickly going, okay, that's opposite over adjacent, which is the same as multiplying by the reverse. Oh, yeah, the 2's cancel out, giving me root 3. So it must be pi on 3. That's what theta hat equals. Any questions before I move on? No, okay. So now that I know what theta hat is, I can now return to my, I'll just do another one here just to keep it clean. But normally I'd probably use the one with the ticks on it already. But I just draw my axes again. I know where the angle needs to end up. It either needs to end up in that quadrant 2. So the angle either has to be here, or it has to be in quadrant 4. So I'll do that in green. It has to be sort of like here. Oh, that was a bit rough. Like that. It's one of those two. And I know that theta hat is in here. Okay, so that's another good reason why I like using that theta hat notation, because I can just stick theta hat where it belongs, and now I can work out where the actual angle is. So we've got this angle here. Angle 1 is this angle, and angle 2 is this. So we don't have one solution, we have two solutions. Okay? Note that theta hat is always, always, always taken from the x-axis for reasons I've said before. It's from the x-axis. So you've got only two spots you can put that. Now I just do it, right? So I do the next bit in my head. I'll verbalize it, but I won't for the video, and I'm not going to write it down. So therefore, theta is equal to, well, it's going to be pi minus pi on 3. Yeah? So pi is 3 pi on 3. So that's going to be 2 pi on 3. 3 pi on 3 minus 1 pi on 3 is 2 pi on 3. What's the other one? I'll start off the thinking. I'm going all the way around to 2 pi, and then I'm going back a pi on 3. 5 pi on... No, what did you say? It's got to be on 3.
Yeah, but then it's 2 pi.
Yes. Oh, sorry. I thought you said 5 pi on 6. 5 pi on 3. Yep.
Oh, yeah, on 3, sorry.
Yeah, cool. 5 pi on 3. Yes, everybody? Again, to explain very briefly, 2 pi to here. So I need it to be on 3, so I make it 6 pi on 3. That's what 2 pi is. And then I take away a pi on 3. That leaves me with 5 pi on 3. Boom, boom, shake the room. So there are two solutions in 0 to 3. If I had said theta between 0 and pi on 2, there would have been no solutions because there's no angle that will give me negative root 3 between here and here. If I'd said between 0 and pi, actually, I'll use this one with the arrows in it to describe what I'm saying. If I said between 0 and pi, that would have just been one solution. If I'd said between 0 and 4 pi, that would have been 1, 2, 3, 4 solutions. So the size of the domain here very much affects how many solutions you're going to have that work. But all you have to do is exactly the same thing. You basically have to work out where is it going, where does the angle have to land for it to be a solution? What's the reference angle? And therefore, in my rotations, however many there are, in my rotations, how many of them fit? In this case, there were two solutions. Any questions? Okay, I'm going to pause the video and you're going to do question 4. I'm going to give you a couple of minutes to do that. In example 2, you're asked to find tan theta if sine theta equals minus 3/4 if theta is between pi and 3 pi on 2. Now, note that you are not asked to find theta. This is a paper 1 question, non-calculator. You can do this without a calculator. However, 3/4 is not one of your usual angles, right? One of your exact values. So it's not 30 or 45 or 60 or 90 or 180. etc., etc. So not one of those, because you don't need theta, you need tan of theta. Here's how we do it. What we do is we say sine of theta is -3/4 and theta is between pi and 3 pi on 2. So we know that the angle is going to be down here somewhere, because that's pi and that's 3 pi on 2. So it's here somewhere. So what I can do is I can construct a right angle triangle here, and then I've got theta hat in the corner there. Excuse me. And I can basically, I'm going to drink, look at the triangle with theta hat here, and I can use my basic right angle trig. I would have opposite is 3 and hypotenuse, oh man, I've screwed that up. Give me a sec. I could do it without a calculator, but the numbers aren't nice. So forgive me while I change the problems ever so slightly to -3/5. It's just to make it a neat problem. I could have left it at 4. So I've got, sorry, opposite 3 and hypotenuse 5. Are we okay with that? I've just pulled out that triangle. Reference angle is always an acute angle. So I can just, and because the ratios are always, doesn't matter how small or big the sides are, I can just pull it out and make it a 3, 5. And so now I can work out what this side is using Pythagoras' theorem. Sorry. So I've got a 3 and I've got a 5, and then I've got this adjacent side. Can anyone know off the top of their head what that side length would be? Yeah, 4. It's a Pythagorean triple. It's a 3, 4, 5 triangle. Now, let's just say you didn't know that or had forgotten that. Then you could just go, let that side be, what do you want to call it? X. You'd say x squared equals 5 squared minus 3 squared. That'd be 25 minus 16, which, 25 minus 9, which equals 16. So therefore x equals 4. Okay, so you could do it by hand if you had to. But knowing your Pythagorean triples is useful. This is a 3, 4, 5. Okay, so what does that mean? It makes it nice and easy, doesn't it? If that's the triangle here, that means tan of theta hat. Oh, how do I fit this in here? I'll put it over here. That means that tan of theta hat is equal to opposite over adjacent. So that's 3/4. Yeah? And therefore tan of theta is what? It's going to be the same value, remember. So it's just, is it going to be positive or negative? So we look at where the quadrant is here. What's positive here? All students take care. So tan is positive here. So tan is also 3/4. Does that make sense? Just as an additional, also cos theta would be what? Negative because it's in quadrant 3, and 4/5 because that's the ratio from our right angle triangle. What do you reckon? Is that doable? Okay, I'm going to give you 5 minutes. No, not even that. I don't even know if you need that much time. It's just question 5. So I'm just going to give you a few minutes to try question 5, and then I want to look at some Pythagorean identities. So question 5. I'll just do this first. A trig identity is really just a kind of like a rule which allows us to state a relationship between the trig functions, I guess. And we're going to look at 2 basic identities today. And in Friday's lesson, we'll also have a look at something called the double angle identities as well. There are heaps of identities out there, so we only need to look at a few for Maths ASL. So the first one is this one, and I'm going to use the unit circle kind of definition here. So we're looking at slide 5 here. I've got a hypotenuse of 1. So what do we know about this side here? What's the value of this side if the theta is here? No. We don't know that if theta is 30 degrees or 40. This is just a general angle theta. It's from our basic definitions. You know, what's this coordinate point here on the unit circle? No. No.
Sine theta, cos theta. No?
Yep, or other way around though. So that's the coordinate cos theta, sine theta, isn't it? So what's this distance here? The vertical distance? Thank you. My goodness me, I'm really worried about this. This should be second nature now. And this distance here is cos theta. Yeah? So what can we say about tan theta? Well, it's opposite over adjacent. Tan theta equals sine theta over cos theta. Yeah? We looked at this last lesson actually, which is, I'm just showing you how to do it from the unit circle rather than from opposites and last time we multiplied top and bottom by the height and stuff like that. Okay, second basic identity is this one here. So again, what's this distance here? Sine theta. There should be a chorus at this stage. It's literally on the triangle right above you. I should have everyone going, yeah, it's sine theta. We just did that, Richard. Not sine theta. What about that bottom distance? What's that? That's better. And there's almost a resentful tone there too, which I really appreciate as well. Okay, Pythagoras' theorem states what? Yep. Between a lot of you, you got it there. And you even had the notation right, which I don't think we've discussed formally. So we've got the square of one side plus the square of the second side equals the square of the third side, of the hypotenuse, sorry. So the square of one side plus the square of the other side is equal to the hypotenuse squared. Now, I don't know where you came across this notation because some people were saying this notation directly, maybe from Maths Extended days, I'm not sure. But in mathematics, because we use so many brackets and stuff, we do try and eliminate brackets when we can, which is why you'll see that here and here and here. This does not mean tan times theta. It means tan's still the function and theta is the value we put into the function. But they are so common, we sort of ignore the brackets. And similarly, we can get very bracket heavy here as well. So the notation is to put the square at the function. Sine squared theta plus cos squared theta is equal to 1. And that's called the Pythagorean identity. Okay, sine squared theta plus cos squared theta is equal to 1. Am I making sense? What's 1 squared, Lily? So to answer you quite directly, yes, it is still 1 squared. But 1 squared is 1. Does it make sense, everybody, where it comes from? Utilising it is where it becomes tricky. So next slide. I'll give you one example, and then you can have a go at doing stuff yourself. So these, you often have to prove identities. And here's an identity that I prepared earlier. 1 plus cos squared theta. So remember, that means the value of cos theta and square it. Okay, so let's just say it was cos squared 45. That would be not squaring 45, but cos 45 is root 2 on 2. So you'd square that and get 2 over 4 or a half. Okay, so you're squaring the result, the output. So in this case, it's 1 plus cos squared theta prove that 1 plus cos squared theta equals 2 cos squared theta plus sine squared theta. Now, you might remember from our proof unit that you only deal with one side of the equation and then you work on it until it's like the other side of the equation. Choose one or the other. Technically, you can work from both sides and find a common spot in the middle, but you never, like subtract one from both sides and stuff like that. So I'll start on slide 10, I think. Left-hand side is equal to 1 plus cos squared theta. Now, I've only got two rules at the moment that I can use. I can either use tan theta equals sine on cos, and that doesn't seem to make sense, or I can use sine squared plus cos squared is equal to 1. Okay, so, all right, well, I've got a 1 there. So let's replace the 1 with sine squared plus cos squared and see what I get. Oh, hang on, that's pretty easy then, isn't it? So now I've got my 2 cos squared thetas here. I've got one of them and then another one. So there's my 2 cos squared thetas. And my sine squared theta. And that is the right-hand side. And that's a pen drop. Put a square box there or QED, something like that. Yeah? Now, one thing I'll just point out, guys, is I'll flick back to this screen in a second if you haven't quite got there, that you won't always be utilizing the identity in that form, because you can also see that sine squared theta is equal to 1 minus cos squared theta. Can you see that? Also, that cos squared theta is equal to 1 minus sine squared theta. So there are different versions of the same identity. You might need to rearrange the identity in order to utilize the fact in the identity proof. Okay, I've got a worksheet which I will put up on Google Classroom as well if you want it, but I'll hand out a worksheet now, and your job is to work your way through these proofs.